Hello, everybody. Welcome back to Math 100, Liberal Arts Mathematics, and this is lesson number 14. Lesson 14 is the last and the third of the three lessons having to do with chapter 5, statistics, right? So this is the last lesson on statistics, and it's called the normal distribution, which has huge implications in decision making, as I have been talking about. And so today we'll be talking about the percentiles and various other topics related to the normal distribution. Again, it has lots of applications, and it does influence many things in our everyday life. All right, so let's go and study the normal distribution, lesson 14. All right, so lesson number 14 is a quick survey of what we call the normal distribution, right? You probably know about the normal distribution in terms of this word, the bell-shaped curve, right? Because normal distribution is characterized by such a curve, all right? And so you can see the curve right here, right? And so this is what the normal distribution curve looks like, and it does look like a bell. And anytime you have this specific kind of a curve, it's called normal distribution. Actually, there's a lot more technical definition for it. And that, by the way, involves things like pi and interesting other numbers like e. But you can just imagine that when we talk about normal distribution, we are referring to the data that is spread just like this bell-shaped curve. And what is it used for? Okay, and it turns out this is a very common distribution. In fact, let's go ahead and start noting this, a normal distribution, also called the, and it is named after one of the most famous mathematicians in the history of mathematics, Gauss, Carl Friedrich Gauss, a German mathematician from the 19th century. And so he, among many things, he studied this particular curve extensively, and sometimes it's called the Gaussian distribution or the normal distribution, the same thing. And what happens is, as it turns out, it is the most common and the most relevant or an important probability distribution. There's a reason for it, okay? And the reason is called the central limit theorem. And what this says is, you know, in the basics of statistics, we learned that many things, many populations are studied by taking data from a sample, right? So when you take a sample, the thing that you are interested in may not be distributed normally, okay? It may not have the same distribution, but this theorem tells us that when you take samples, okay, you take a bunch of samples and you find the sample mean for each sample. And of course, depending on which sample you take, okay, you end up with a different mean. And those means, the sample means, are going to be distributed in this normal way or normal distribution. And that's what this theorem tells us. And that's why this normal distribution is playing such an important role in study of statistics. All right, so the curve is, like I said, it's bell-shaped. And what's very important here is that it is symmetric. And symmetric means that the right-hand side and the left-hand side looks exactly the same. Here's the right-hand side and here's the left-hand side. The mean and the median are all in the same place. Where is it? It's right in the middle. And so the 50% below and 50% above the mean. Okay, so when a quantity is normally distributed, half of the values are to the right of this, and half are to the left. Okay, and we assume that each point has no value. Okay, in other words, we just assume that everything is to the right or to the left of each point, and so you can say 50 on the right and 50 on the left. All right, so one of the important rules that is related to the normal distribution is this thing called the empirical rule. It also has a funny name. It's also known as the, ready for this, 68, 95, 99.7 rule. Yes, that is the name. The name of this rule, often called the empirical rule, empirical rule is sometimes called the 68, 95, 99.7 rule. And of course, these are not just randomly generated numbers. They do have a meaning. So many quantities are normally distributed. And you will see a bunch of examples as you do your homework and as you work on your worksheet. Okay, but the mean, we denote, and this is a little Greek lesson here. Yes, Greek. The mean is often denoted with this mu. Okay, so this is the Greek letter that corresponds to our m, mu, and then the standard deviation starts with S, and so the corresponding letter to our S in Greek is sigma. That looks like this. Okay, it's like a zero with a tail on the top. All right, so whenever I write sigma, think of that as the standard deviation, and mu is the mean. Okay, so these are the two things we learned in our last lesson. And so they play a major role in the study of statistics and the normal distribution. Okay, whenever some quantity is distributed normally, and it could be height or weights, or let's see, the length of something. The length you have to wait at a certain bank, or maybe it's the distribution of income at a certain level of the society or whatever. Okay. Anyway, about 68% of the data are within one standard deviation of the mean. Right now, remember, mean is right in the middle, right? Mu, right in the middle because of the symmetry. And then if you add one standard deviation to it, you get this mu plus sigma. I know it's hard to see on the screen, but this number is mu plus sigma. It's one standard deviation above the mean. This number, mu minus, so here, let me go ahead and write this. This is mu plus sigma, okay? This is mu minus sigma. So that's one standard deviation below the mean, okay? What this first part is saying is that if a quantity is normally distributed, then within one standard deviation from the mean, so from here to here, okay, you have 68% of the data. About 68% of the data are within one standard deviation of the mean. How do they know this? How do you know this? Well, somebody actually did the calculations, including Gauss, and we have a very mathematically precise definition of this normal distribution. It is a certain function. It's called the standard normal function. And so you can actually calculate the area under the curve using calculus, right? And so they have discovered that between mu minus sigma and mu plus sigma, which is one standard deviation below and above the mean, you have 68% of all the data, okay? And then if you go to two standard deviations, so this is mu plus two, sorry, not plus two, mu plus two sigma. And then this is mu minus 2 sigma. So if you go within the two standard deviations, so mu minus sigma to mu plus sigma, that's two standard deviations from the mean, then you have 95% of all the people, or all the populations, or all the data, right? So again, 68% within one standard deviation, about 95% within two standard deviations. And if you go to a 0.3 standard deviations below the mean and all the way up to 3 standard deviations above the mean, that's 99.7% of all data within three standard deviations. And that's pretty much all of it, right? Pretty much everybody. Not quite, because you're missing like 3 people out of every 1,000. But that is a lot of people. And so that's where the name came from. The empirical rule is called the 68, 95, and 99.7 rule. Even though the name of the rule is the empirical rule, it is not based on observation as much as in precise calculation. That's why we can come up with these precise numbers, okay? As I said, this is the curve that sort of dictates the world, right? Lots of major decisions in government to industry to corporations, whatever. They are made based on this normal distribution because this tells us, you know, the percentage, also the risk. the chance, the probability, right? All those things depend on this one normal distribution curve. All right. So as you can tell, now how do you know, like, if my score, let's say, here is the distribution of a test score or something, and it is something big, like maybe SAT test score, maybe IQ test score, maybe ACT test score, whatever, okay? And they are normally distributed. And how do I know that my score is over here or here? How do you know that how many standard deviations above the mean my score is? And that is a very important question. Okay, so it is important to know, as we have just looked at it, given any data value, how many standard deviations above or below the mean that value is. Okay, so for instance, if this describes a normal distribution of a test score out of 100, and if the average happens to be 70, and if my grade was 78, okay, what percentile, what percentage of people are below me, what percent above me? To answer that kind of question, we need to know how many standard deviations above the mean this number is, okay? And in order to know that, of course, you have to know the standard deviation. So to answer this question, it's actually not hard, okay? It's easy. You normalize that quantity, my test score, to find what we call the z-score. Okay, the z-score is something that you would spend a lot of time studying if you were taking the full semester statistics course, Math 140. But here, I will just refer to this z-score with this formula, and I hope the formula makes sense. Okay, and after this, we will do some practice, and this will be intuitive. This will be easy to find. All right, so if your x is the your score, one's value, all right, and the mu is, of course, the mean, right? And what happens if you do x minus mu? Well, if my score is 78, and if the mean is 70, the numerator here will, of course, be 8, right? Because 78 minus 70 is 8. And so that's the top, and then you divide it by the standard deviation. This clearly, and I think you can understand it, this clearly tells you how many standard deviations above the mean this is. So if the standard deviation of this distribution is 4, okay, then you go 74 and then 78. That's 2 standard deviations above the mean. Get that? Right? So, and every 4 points, you have 1 standard deviation higher if sigma is equal to 4. So this clearly tells you the standard deviation. I mean the z-score, and z-score tells you how many standard deviations above the mean that value x is. All right, so remember the top is called the deviation. That's the difference between one particular score or the data value minus the actual mean. And then you divide the you divide the deviation by the standard deviation, and that's how you find the z-score. Okay, let me emphasize again, this is not hard. Why is it not hard? I mean, the thing is this, I'm giving you a formula, but you really don't need the formula, right? I don't think. Okay, let me explain. So suppose the test score, some kind of test score, is normally distributed, right? By the way, lots of things are normally distributed, as I have mentioned many times. For instance, somebody's weights are normal, people's weights are normally distributed. If you study people's things like the cholesterol levels or vitamin levels or whatever, these things are also, they tend to be normally distributed. Heights, weights, all those things. Whenever it involves a lot of people, many times the distribution is normal. Okay? In other words, you have lots of people in the middle and not too many extreme values. This is a very typical distribution. We see the normal distribution appearing in many disciplines, many the fields of application, right? All right, so suppose that this test score is normally distributed with a mu of 60 and the standard deviation of 10. Okay, so here's what you can do. Here's 70, that's 1 standard, this is mu, and mu plus sigma would be 10 more than 60, right? And then 80 is here, that's 2 standard deviations above the mean. And because the sigma value is 10, if you go backwards and subtract 10 from 60, the average, then you get 50, which is 1 standard deviation below. And then this is the 2 standard deviations below the mean, right? All right, so these are what we call the X scores. And you can convert them or normalize them. That the term is to get the Z-score. Normalized it, 60 becomes 0. Why? Because every time you have a normal distribution, the mean, by definition, right, the mean is mu. So if X is mu, this part becomes 0 and Z is 0. The mean has spelling it wrong. The mean always has the Z-score of 0. By definition, we want, because you're asking like how many standard deviations above the mean is this number X. And so if X happens to be the mean, of course, the mean has the 0 Z-score because the mean is 0 standard deviations above the mean. All right, so the Z-score here is 0. You can see the Z-score for 70 is 1, and the Z-score for 80 is 2. This is -1, -2. You see that? I didn't even have to use this equation because 10 is a pretty simple and nice number. All right, did you get that? So here's the way to think about this. The Z-score corresponding to 60. Maybe I should explain the notation. When I say Z of X, this is the Z-score for the value X. Okay, so X is 60 in this case, meaning 60 points on the test. X could be 6 million if 6 million is a standard number, like the mean for something. Okay, X could be a very large number, very small number, but the point is when you change them to Z-score, the mean becomes 0, and so the Z of 60 is equal to 0. Okay, Z of 70, now remember, because 70 is exactly 1 standard deviation above the mean, this will be 1. Z of 80 is 2, and Z of 50 is -1, and so on, right? So what is the Z of 65? 65 would be right here. Okay, if you get a 65 on this test, what is my Z-score? How many standard deviations above the mean am I? And this time you can use the formula if you like. It's 65. Remember this number minus the mean divided by the standard deviation of 10. That's 0.5. And that's because 65 is exactly 50% more than the, well, let's say it's half of the standard deviation above the mean. That's what 65 is. Right? If I have a test score like 73, then I can plug this into the formula. 73 minus 60 divided by 10. That's 13 divided by 3. 1.3 is my Z-score. Okay, so I'm saying that 1.3 is the Z-score corresponding to the data value of 72. Right. Now, so you can see that X could have all kinds of numbers, small, large, whatever, okay? But the mean plus the standard deviation will give you the Z-score, which is standardized, right? So whenever we use a Z-score, the graph will look more like this. Z-score is always 0 in the middle, and 1 here, 2 here, 3 here, -1, -2, and -3. And based on the empirical rule, or according to the empirical rule, this is pretty much all you have to consider, because between here and here, you have 99.7% of all the data points. All right, because, okay, so based on the Z-score, we can use the standard normal distribution, and that's the one I just drew here. Okay, and what makes it the standard is that the fact that X could be 60 or 70 or 80 or so on, but when you normalize the X score and convert the X scores into the Z scores, then you always have 0 in the middle, and then 1, 2, 3 above, and -1, -2, -3 below. This is called the standard normal distribution. This is found on page 196 of the book, and it comes with a table. What do we mean by a table? Let me show you the table. This is a part of a table. It's not complete by any means. And you can find this in the book on page 196, and we will be using this to answer some very important questions on the percentages, on the probabilities, and on other related topics, okay? So this is going to help us calculate exactly what percent of the data are below and above that particular data value. And that will help us find the percentile as well. Okay, so here is the original design of what has later been known as the SAT score, the Scholastic Aptitude Test. In some states, in order to go to certain colleges and universities, they required SAT score. You see, it has just recently announced that they are no longer going to use this and so on. But anyway, each part of the SATs, this is like the entrance exam test for the United States, even though that's technically not the entrance exam, right? Each part of the SAT score in its original design, okay? And you know, the SAT score, I mean, that's just like, they have raw numbers and we don't know what those numbers are. But what they do is they normalize those numbers. Okay, so there are some students who are really good and there are students who don't do so well. And if you get the raw scores, that becomes a normal distribution, right? And each part, I mean, like math is one part, English, well, actually verbal and quantitative. And I think for some time they've had essay part as well, or writing, okay? But each of those parts of the SAT score was designed initially so that by design, the mean was 500. So that's exactly where the average person is. And then the standard deviation was 100. So that means 600 here, 700, 800. That's 3 standard deviations above the mean, right? So these are the X scores. And of course you have, you know, from 200, 300, and 400. Okay. And remember I said within 3 standard deviations, you have pretty much everybody. Okay. And so by default, that's what they decided to do. 200 is the least number you can get, and 800 is the perfect, right? So if you score perfect, nobody's going to get more than 800 on the SAT score because this is considered the perfect number. And that's because they assume that, you know, 3 standard deviations above the mean is the highest number that a person should get. All right, so let's find out the Z-score for 500. If you got 500 on the SAT, then your Z-score is 0, of course, okay? Because this is the mean. If you get a one part of your score, well, the score of one part is 600, then of course this is 1 standard deviation above the mean, right? Because the standard deviation is 100. Now, of course, if you want to use the formula, you can do this. Okay, 600 minus 500, that's the deviation. Divide that by the standard deviation, that's 1. Okay, so the score of 600 is considered to be 1 standard deviation above the mean. If you didn't do so well, and let's say you got 300, then 300 minus 500 divided by 100 will give you -2. And that means, again, 300 is 2 standard deviations below the mean. That will put you as, you know, below the average student. Okay, so that's how they calculate these things. Now, why do we talk about the Z-scores? Well, because Z-scores tell us the percentile and the percentages of students below and above. Right? Now, how do you do that? And I'm glad you asked because I'm about to answer that question. And the answer comes in this table here. Okay, now this is the table and I will show you. I am going to provide this on our website in Canvas, but there's a more extensive, see that more extensive standard normal distribution table. It looks like this. Okay, every statistics book has one of these. And of course, most recently, you know, these things are embedded in, you know, scientific and statistical and graphing calculators. So your graphing calculator, if you have one, has all these numbers embedded into their program. So they can tell, for instance, what is the probability that the score of something that's distributed normally is between, you know, 500 and 800, for instance, for SAT score. All right, so this is a simpler version of it. It doesn't cover all the problems, but let me explain using the simpler one, how you can use the table to come up with various percentiles. Okay, so what percent of the scores are, I'm still talking about the SAT, right? Let me go ahead and try to describe this again, right? Oh, you may want to practice drawing this. You see how nicely I can draw this? This wasn't that pretty, but and you try this, it's really hard to draw a very symmetrical. This was really nice. Okay, and the idea, the key is this: don't draw this thing first and then try to do this, because it's really hard. Draw your bell-shaped curve first. Okay, I mean after the horizontal line, and then draw the line in the middle. It's a lot easier if you do it this way. Okay, so we understand this is 500, right? And then you have 600, 700, and 800 is the maximum as far as this is concerned. All right, the question here is this: what percent of the students score between 500 and 600? So we're talking about this area. Okay. Now realize that these are the X values. Okay, so these are the scores you get out of 800. And between 500 and 600, what you have to do then is to convert these to the z-score. Okay, so 500 by default, because 500 is the mean, gets 0. 600 has a z-score of 1, right? So the question I just asked, what is the percentage of students who score between 500 and 600 in every part of the SAT score? The answer, actually, the question can be switched to this question: what is the probability that a randomly, what is the probability of a value that is normally distributed being in the z-score, between the z-score of 0 and 1? Okay, that is the question. And the answer comes in a chart like this. So between 0 and this z-score, in this case, it's 1, right? So you look at this 1, and this will give you the number or the probability or the percentile or the percentage of the values between this 0 and the z-score that you chose. So between 0 and 1, you have 34.13%. You see this number, 0.3413. Of course, that's written as a decimal number. But if you change that to your percentage, you can see that between 500 and 600, which is the between these scores of 0 and 1, you have 34.13% of all the students. And that's the percentage of the whole who scored between 0 and 1 in terms of the z values. Okay, how about less than 600? Okay, watch carefully here. What about the percentage of people less than 600? Now notice here, the table told us this part has 34.13%, right? But when you say less than 600, guess who else is included in here? Everyone around here. These people also scored less than 600, right? And what percent is that? To the left of the middle? Yeah, it's exactly 50%. So in this case, you have to add 50 to this number. I don't know why I'm adding the percentage on this one. But the answer is going to be 50% more than this. It's 84.13%. Okay, so you could make the statement based on these assumptions that 84.13% of all the students taking this SAT test is going to score less than 600 on this particular area. Get that? Yeah. All right, so now let's answer this question here. How about between 300 and 500? 500 is the middle, 300 is down here. Okay, now remember the z-score of 300 was -2, right? So you have -2 here in the z-score column and 0 here. We are looking for the percentage of data values belonging to this region between the z of -2 to z and z is 0, right? Well, this part is to the left of this, so it's not quite this, but that's okay because it's symmetric, right? All I'm looking for is what is the percentage of values within the two standard deviations only on one side. So I look at this number, that number will give you what percent of the data values are within, well, between the mean and the two standard deviations above the mean. The answer is 4772. So here, the answer to this question is 47.72%. Okay, and that comes from this number right here. Okay, so you can say that between 300 and 500, we have 47.72% of all the students who took the SAT test. So that's how it works. Okay, by the way, I forgot to mention one more thing here. And because I didn't write it down. I said in number 2 here, I said here, people who scored 600, okay, let's say here's a student who scored 600 in this one area of SAT test. According to our assumptions, 84.13% are below the student, which tells you then what's 100% minus this. Okay, this will be 15.87%. So only 15.87% of the students who took the SAT test with him or her is above or are above this, right? And so that's going to put him into, well, actually, this is, I mean, you can say top 16%, right? So this student is a fairly good student in top 16% of his class. But you could also say, using this, this refers to the, you kind of ignore this decimal part. It's called, he or 600 is called the 84th percentile. The word percentile, the strict definition is kind of hard, and it varies from book to book, but it is basically the number of percentage, the whole number percentage, okay, without the decimal, the whole number percentage of all the data below a particular number. Okay, so if you scored 600, then at least 84% of the people are below you, more precisely 84.13%, then you will say, or people will say, you are in the 84th percentile. Okay, so that's the that's how we can define a percentile. Don't worry too much about the percentile, but you do need to know how to answer these questions. All right, let's go to the next one. Another test question. The original IQ, when the intelligence quotient was proposed almost 100 years ago, I think it's a little over 100 years ago by a psychologist, they came up with this idea, okay, because intelligence, you know, but basically what you do is students, kids, basically ask a bunch of questions, pattern recognition, you know, recognizing other things, not exactly reading and writing and all that, but can they understand certain patterns? And then you answer these questions, and usually there are lots of questions, and they get a raw score, okay? But then they normalize this in some way. And so what they have done is traditionally, or in the initial proposal, they decided, you know, let's have a nice number for the average. So the average is called 100. So the mean is 100. And by the way, this means that your mental or intelligence age is exactly the average of all the people in your chronological age. Okay, that is defined as 100 on the IQ scale. And the standard deviation was 16. Okay. So that means if you're right here, 116, you are exactly one standard deviation above the mean. 16 times 2 is 132. So 132 is considered 2 standard deviations above the mean. These are the X scores. Converted to Z scores, this is 0, this is 1, this is 2, as before. Right? So let's calculate the Z-score for 100. Well, we didn't have to do that because this is a mean, so the Z-score has to be equal to 0. Get that? Right. Try to find the rest of this, all right? And then I will come back and discuss the rest of this when you go into the next ones. I want you to find this, this, and this, and see if you can answer these questions, right, before we go into the next segment of this lecture video.